Professor Anna Scaife, welcome.
Yeah.
So, you wanted to be an archaeologist when you were younger. I wonder at which point you decided that you wanted to shift your focus from what's in the ground to what's in space.
Oh, that's actually quite an easy one to answer. I think I was disproportionately influenced by Indiana Jones films when
Really?
when I was very young. Yeah, loved Indiana Jones, and so archaeology seemed like a solid career choice.
Mm-hmm.
You know, when you're 12 and you're watching Indiana Jones, and then there was a TV show called Time Team on Channel 4, which sort of followed around a group of British archaeologists doing digs all over the country. Which put archaeology in a somewhat different and probably more realistic light.
Yeah.
And I decided that maybe it wasn't quite the exciting, adventurous career that I had I had first imagined. And yeah, I didn't switch to astrophysics immediately at that point. I just decided that I wanted to do something other than archaeology.
So when did the astrophysics come in?
Not really until the end of my undergraduate degree. So I did an undergraduate degree in physics, and in the fourth year of my undergraduate degree, much like in the fourth year of the undergraduate degree here in Manchester, I did a research project.
Okay.
And I did an astrophysics research project, and I really enjoyed it. And it was quite a technical radio astronomy research project, and that just sort of set the course of my career, I think.
Mm-hmm.
Yeah.
I know you're very deep into the field. So you've been really heavily involved in something that's known as the Square Kilometre Array project.
Mm.
Now, I feel like with a lot of these astrophysics projects, they tend to go, pun intended, under the radar. People kind of don't know what's going on until the really big stuff happens. Could you summarize what this project was? Because it seems to be a pretty big scale sort of thing.
Yeah, so the Square Kilometre Array is basically the world's next big radio telescope.
Yep.
And it really is the world's radio telescope because it's a collaboration between, gosh, I've lost count of the number of countries, 16 or 17 countries at this point. It's sort of like CERN is for particle physics, but for radio astronomy.
Okay.
And it's a project that has been in the sort of the design and development stages for a long time. These things don't happen overnight. And as it's grown in its design, it's evolved, and we now know exactly what it's going to look like because it's set to start taking scientific data in a couple of years' time. And so the final realization of the Square Kilometre Array is that it's two radio telescopes, one of which operates at very low radio frequencies. That's very long wavelengths, sort of wavelengths of radiation that are the same length as a double-decker bus, for example. And that telescope is going to be based in Western Australia. And then the second telescope is a telescope that works at shorter wavelengths in the radio spectrum, and that's going to be based in the Northern Cape of South Africa. And they're called the SKA-1 Low and the SKA-1 Mid. The one being in there with the implication that, this is a project that could evolve. There might be more telescopes. And then, of course, the observatory is the organisation that runs the telescopes.
Right.
And the headquarters for the observatory is here in Manchester.
Okay.
Yeah, it's not part of the university. It's its own organisation. In fact, it's somewhat even outside the country, in spite of the fact that it's physically based at Jodrell, because it's an intergovernmental organisation. So it's a truly international headquarters for the telescopes.
What's the actual ambition for the projects? So is it? I assume it's not just put telescopes up and see what you can find.
No.
Trying to find something specific.
Of course not. Yes. Yeah. So there are a number of high priority science objectives for the telescopes, and it's those scientific objectives that have governed the design. It's why we have two different telescopes under one observatory. In fact. Probably the original driving science case was to detect something that's known as the epoch of reionization.
Okay.
Which is it's the
point. Have to explain that one.
Yeah. It's the point in cosmic history at which stars and galaxies started to form. So when we think about the universe around us, we actually know quite a lot about the beginnings of the universe because there have been a number of observatories and experiments that have observed something called the cosmic microwave background, which is the first visible light in the universe. But that is, as the name suggests, a background. It's background radiation. That was essentially the start of the physical universe. After the cosmic microwave background, which is when light decoupled from matter and started to become detectable, the universe was basically empty. And there was this period of cosmic history that was known as the Dark Ages, when, there was really nothing around. It was largely just hydrogen and a few trace elements.
Okay.
And then after some time, there was a point in cosmic history where, as a culmination of circumstances, actual substantial objects started to form. So stars, galaxies, black holes. And that point in time is the epoch of reionization.
Epoch of reionization.
Yeah, we call it the epoch of reionization because during the dark ages of cosmic history, the universe was largely made up of neutral hydrogen. So hydrogen is the most abundant element in the universe. It's a very simple atom, and you can ionize it by kicking an electron out. So if you can hit a hydrogen atom with a photon of enough energy, it kicks the electron out and you get a charged hydrogen atom. So you have an ionized atom. So when the first stars and galaxies started to form, they produced this radiation that caused the hydrogen to ionize.
Yeah.
And so that first epoch of ionization is it's like the key tracer of star formation and galaxy formation. So if we look at the universe that we live in today, there's a huge amount of ionized hydrogen, right? And we have stars and galaxies and black holes and everything. So we know that there must have been a point in cosmic history when all of this started. We know roughly when it is in cosmic history, but we don't know exactly when it happened, and we don't know exactly how it happened. Right, so it's a question, was it stars that were formed first? Was it black holes that were formed first? How did it happen? How fast did it happen? That was the sort of the originating science case for the Square Kilometre Array. And it's where the name comes from. So there was a calculation done about how sensitive would a telescope need to be to detect this epoch of reionization, because it's very distant in terms of cosmic history. So you need a very sensitive telescope. And the sensitivity of a telescope is largely governed by the collecting area of the dishes, essentially. So the physical size. And the calculation was that we would need a square kilometre of collecting area to be able to detect the epoch of reionization.
Could you put that into like a comparative of what that area looks like?
Well, it's difficult to visualize really because, what is a square? I literally don't know what a square kilometre looks like. I can't think of something that's a square kilometre. Maybe you have a better idea. Yeah, it's sort of big. It's not giant, right?
Yeah.
It's not planet-sized or anything. So it's achievable, right? That's the first thing. The reality is that the telescope that's being built is going to have more than a square kilometre of collecting area, because as soon as you start designing a big telescope, other people come along and they're like, well, we could also use it to do this thing as well. And then your science case gets a bit broader. You change your specifications very slightly so that it can accommodate other people. And then eventually enough people have come along that you really have to reevaluate your whole science case completely. And that's what happened for the SKA.
Well, I'm interested in this sort of origin of galaxies, effectively. So the universe begins, whatever that means. There's seemed to be some sort of Big Bang-like event.
Yeah.
Seems like for a long time. So is it billions of years that the universe was essentially pretty inert? Sure.
Now you're asking. I don't actually know what the number is. I couldn't even put a number on it. It's not. So I should say it's not my research area.
Yeah.
It's just I know about it because it is so prominent in the general astrophysics community at the moment. But the basic picture, going from Big Bang to now, is that there's the Big Bang, and And then there was a period of rapid inflation where the universe expanded very, very rapidly and eventually expanded to the point where the temperature of the universe cooled down sufficiently for photons to escape from baryonic matter, so normal matter, if you like. And that's where we get the surface. It's called the surface of last scattering. That's the name where those photons escaped. And that's where we see the cosmic microwave background. So that's literally the first visible point in the universe. Before that, the photons, the light, was literally bound into the baryonic matter. So the only reason you can see something is because you can collect photons with your eye or with your camera. If the photons can't travel towards you, you can't see it.
Yeah.
So at that point, the photons escape. We see the cosmic microwave background, and the cosmic microwave background provides an imprint of the state of the universe at that point in cosmic history. And then after that point, the universe continues to expand, but at a slower rate. Yep. We have these dark ages where the universe is basically neutral hydrogen, and nothing's really going on until something happens sufficiently. So some overdensity condenses into a star, some kind of nuclear processes happen within that star to stop powering it. We can start to get galaxies, possibly black holes, because the earliest stars, the hypothetical earliest stars, were very short-lived. So if you have a very massive star that dies, you get a black hole. So that point in cosmic history, we get the first stars and galaxies, and then from then on, it sort of evolves into the universe that we see around us today. So it's an interesting thing about astrophysics, I think, which is that when we talk about distances, we're also talking about time.
Yeah.
Yeah.
So this ionized hydrogen that's so abundant in the universe, what does that actually sort of do per se? Like, how is that changing the way the universe is?
Yeah, so it's important for all kinds of things. So the universe is basically a giant laboratory filled with gas. Yeah. And the ionized hydrogen is important for a huge variety of processes. So firstly, so I think probably some of the most important ones are the way, so once you have an ionized gas, it can interact differently between different types of ionized species, if you like. And also the other thing that I think is really critical is its interaction with magnetic fields. So charged particles obviously interact with magnetic fields through basically the Lorentz force. And magnetic fields are absolutely crucial for controlling a whole variety of processes within the universe, from everything from, stars being born within galaxies to, in fact, how the large-scale structure of the universe between galaxies is formed and evolved. So there's all kinds of different interactions.
So with a project like this one, with the SKA, or really any sort of similar sort of astro projects, whether it was telescopes or really anything, could you describe just the sheer organizational challenge? I mean, right from the conception of, we have this idea, then sort of drawing the plans, and then the actual engineering of getting the materials, building, putting it, setting things up, and then actually getting data, and then evaluating.
Yeah, so it's a huge undertaking. The logistics of running a large international project to build a facility of this size, a scientific facility of this size, are quite staggering, especially when you have a wide variety of stakeholders. Yeah. Right. So you have the scientific community who are trying to push for different priorities in the design, depending on their science interests. Obviously, the funding flows through national governments, and national governments have their own priorities. And then you have the sort of the wider political landscape around international science as well. So it's got a lot of moving parts. From the early stages of the project, so the early stages of the project are probably the most scientifically driven stages.
Right.
In the early stages of the project, you really have to make sure that what you're building is going to be able to achieve the scientific goals that the community set. And so there's a huge amount of engagement with the scientific community in the early stages of the project. Once you've decided what you're going to build and what it looks like, then it becomes a systems engineering process.
Mm-hmm.
And I think that can be quite a difficult transition for scientists who have been involved in the project, because, you know, to some extent that sort of pushes the scientists aside for a while, just so you can get, and gets the engineers in, so you can actually get the thing built.
Mm-hmm.
And historically, you know, many observatories and experiments in astrophysics have been small enough that, in fact, the astronomers just build them themselves, because astronomy is this science that sits at the intersection of engineering and physics. And especially in radio astronomy, there's quite a high level of technical expertise within the community. But when you come to a project the scale of the SKA, you simply can't work like that, because it logistically it doesn't work. So you have to take this much more formal approach to it. And I think that can be difficult for people.
Yeah, I mean, is this the scale of this project? Is this maybe not the first of its kind in scale, or is it one of the first?
So it depends what you mean in terms of scale. In terms of the size of the radio telescope, it's definitely the biggest. It's the biggest that's ever been done. In terms of the cost of the project, no. The cost of the project is, I mean, it's high because it's a big project, but if you compare it to, for example, single satellite missions, it's not that expensive.
Mm-hmm.
And if you compare it to something like CERN, for example, that's a whole other ballpark.
Yeah.
Yeah.
When people hear telescopes, they think of the lenses that looks out and gets pictures.
Yeah.
You're trying to, obviously a lot of astrophysics is picking up other forms of data. So in this case, radio waves and such.
Yeah.
When you've got this huge collection of data, how are you going from that to then actually building, not a literal picture, but building an idea of what you're trying to see?
Well, so we do make pictures.
Yeah.
I mean, that's it's one of the beautiful things about it. Yeah, I think it's much more conceptually difficult for people to grasp how a radio dish makes an image.
Yeah.
We're very much, you know, as humans, biased by optical images, because that's what we make ourselves. And so radio telescopes don't natively see an image of the sky. It's not like a CCD, it's not like the pixels in your camera.
Yeah.
What we measure with radio telescopes like the SKA, which are interferometric radio telescopes, we measure the amount of intensity on different scale sizes from the sky. So you can think of them as the amount of power at different resolutions on the sky. And then we combine that to make the image. So it's a more complicated process to create the image, but it allows you much more flexibility in what you actually get an image of in the end. So, for example, if we want to make images of, you know, very, very fine detail on the sky, very small objects, for example, or you know, the highly detailed morphologies of a particular galaxy, then that means that we have to only look at those very small scales on the sky, and we don't really care about the larger scale emission. In fact, the larger scale emission might be blocking those little details. It might be clearer if we could just pick them out. So with an interferometric telescope, you can literally select the scales that you want to be sensitive to in advance, and then position the dishes of your array so that you just pick up those scales. To do that, or to make an image like that from any radio interferometer, then relies on having 2 levels of computing behind it. The first level of computing is what we call the correlator, and it combines the signals from different dishes or antennas within the array. And then the second level of computing is when we make an image from that.
Mm-hmm.
And the imaging process is highly dominated by a mathematical transformation called a Fourier transform,
Yep.
which takes the power on different scales and basically creates an image from it.
Right.
So those are the two major parts of the computing that sit behind a radio interferometer. Obviously, the more antennas or dishes you have in your array, then the more pairs you have. And that also means that you have sensitivity to a larger number of scales on the sky, or number of scales in your image. And so the imaging becomes more complicated as well.
Mm-hmm.
So for a telescope like the SKA, in fact, the computing is a really big undertaking to be able to create an image from the data from hundreds of dishes.
Yeah, I mean, I imagine once you've actually conducting the observations, you've got this kind of huge bank of data. And you said before, there's the scientists that conceive the idea, then the engineers come in. Is it then that the computer scientists come in and then try to organize through all that data?
So I'm not sure I would call it computer science. I would call it scientific computing. So it's
right.
It's a sort of there's a nuance in the in the semantics of it. So there will be some computer science behind it, but the imaging processes that we use in radio astronomy were designed in radio astronomy.
Right.
And most of the computing has been largely designed by astronomers as well. Right. So I think if you look at astrophysics and particle physics as well, these are sciences that have historically dealt with huge volumes of data and quite complex computing.
Yep.
And so we have a history of expertise in that direction. Now that is changing, I think, slightly. AI has shifted the balance a bit there.
Yeah.
But it's still the case that predominantly, actually, the computing software behind the telescopes is done predominantly by people in scientific computing out of physics and astronomy. The hardware would be more specialized, I think.
Right.
Yeah.
Well, you mentioned AI, and I don't think we could have had this conversation without talking about it, because it feels like a lot of people hear that AI is doing this, or it's changing this, or it's revolutionizing this field, and I want to know what it's actually doing now. How is it actually changing the way that maybe you're doing the work that you're doing now versus what you were doing 5 or 10 years ago?
Yeah. So AI has had a big impact in astrophysics, mainly because it's such a data-heavy subject.
Yes.
And, when we were designing the computing for the SKA, one of the problems we had is that actually these algorithms that we've used for a long time, they don't scale very well to the data volumes that the SKA is expected to produce.
Right.
And at the time, we had this realization.
Sorry, I want to say, by scale, do you mean that those algorithms become really inefficient as you scale up the sort of input?
So if you look at when you look at the computational cost of an algorithm, you look at the complexity of its complexity with the number of data points, say.
Yeah.
And so if you look at you do the calculation for the number of data points you expect for the SKA, and you suddenly realize that actually, if you take a 6-hour observation of the sky, it's going to take you a year to process the data. That doesn't work.
Yeah.
Right. So things have to change, right?
Yes.
You can make efficiencies, but efficiencies only go so far because there are fundamental limitations because of the underpinning algorithms that you have to use.
You never have a perfect algorithm.
Yeah, exactly. So then we had this realization about 10 years ago now. And at that time, AI was not as popular as it is now. Mm-hmm. This is pre-ChatGPT, right? Pre-language models. And so we were looking for solutions for the astronomy computing. And they just didn't seem to exist at the time. I'm not sure they exist now. There are people working on them. And one of the things we realized is that a lot of the AI development that was done historically had not moved in the right direction for what we needed.
Okay.
And I think over the last 10 years, what we've seen is a bigger push towards what I would call domain-specific AI development.
Yeah.
So AI development that actually takes account of the needs and the particular challenges of a specific scientific field.
Yeah.
Yeah, and rather than just a generic AI solution. And that evolution over the last 10 years, I mean, it's been exponential in the astrophysics literature. If you look at the publications on it, has changed the way that we do astronomy. So the way that a student starting a PhD this year would do their project is, I think, vastly different from how a student starting their PhD 10 years ago would do their project.
So just to reiterate, so you've got this problem where your kind of old algorithms, from a complexity viewpoint, don't scale very well. And so how is using AI going to, how does that actually sort of neutralize that problem?
So you have to reframe the problem.
Right.
So, so you can teach a deep learning model to do so, to basically to mimic the outputs of a known analytic algorithm.
Yeah.
Not because the AI understands how the original algorithm worked, but because it knows how to mimic the outputs. So that's a replacement for traditional algorithms. So we maybe call them surrogate models.
Yeah.
So you can replace a very costly algorithm that you can express analytically with a much less computationally expensive AI model that achieves the same output, but has no physical grounding in its actual, internal mechanisms.
And how well does that scale? Would you not run it into another scaling problem? Because how is that going to...
So the scaling is reversed. In deep learning, typically the thing that is very expensive to do and that you need to work carefully to scale is the training of the model.
Yes.
Yeah. But once you've trained the model, the actual deployment or inference is typically much cheaper.
Mm-hmm.
So what we would be talking about here would be training a model once to replace specific astrophysics tasks, and then using it many, many times, deploying it as a trained model. So the problem is there is still a scaling problem, but it becomes a different kind of scaling problem. Yeah.
And so the original algorithms that you were struggling to scale, is it still the case that, say, mathematicians and physicists are still working on those algorithms? Or
Yes, definitely. So, I mean, those are our ground truth, if you like.
Yeah.
Right? It would be...
It's your sort of frame of reference.
It's our frame of reference, yeah. It's the thing that we can we know how it will behave in different circumstances. It's predictable. It's it's the gold standard, if you like.
And they are proven.
And they are proven, yeah. They are the underlying. They're based on the physics of how the telescope works.
Yeah.
Right? So there's no issue with that, and there are still efficiencies that can be made.
Yes.
And so there are definitely people working on that. And then on the other side, you have people working on the alternative AI models as well.
Mm-hmm.
But you can't have the AI models without the other one.
Yeah.
Because otherwise you have no...
You need something to train it, yeah.
Yeah, exactly. You have... Well, it's not simply just the training, it's that you have no frame of reference, right? How do you know that your model is actually behaving correctly? So it's... you have to have both.
Yeah. Does kind of using AI in this way kind of pose any challenges, let's say, in terms of accuracy or?
Yeah. So so I don't know about accuracy. Well, so I do know about accuracy, but so the performance issues. So I'd call it performance rather than accuracy.
Right.
So the AI models can perform very well.
Yeah.
I think one of the things that we don't have yet from the AI models is a good measure of how confident the models are in what they do.
Okay.
So, for example, I could train an AI model to produce an image from a radio telescope.
Mm-hmm.
And perhaps that image is very, very accurate in the center and then less accurate at the edges. The mechanism for the AI model to be able to tell me that is something that is not yet done as standard.
Yeah, it's kind of a meta question.
Yeah, well, it comes down to how you build your AI as well. So it's literally just part of the program, but because of the complexity of how deep learning models work, it's actually quite difficult to get a reliable measure of, I would say, uncertainty rather than confidence in the things that they predict. And everything an AI model gives you is a prediction, right?
So is there a lot of sort of intersection between, let's say, the computer scientists and the AI engineers and physicists and mathematicians?
So increasingly, yes. Yeah, so you'll see a lot of interdisciplinary teams now emerging. It used to be much more siloed. But these days, I think there's much more crossover. And it doesn't necessarily end up being that you have a computer scientist working with a physicist, working with an AI engineer. You have someone who has trained through their PhD and their postdoctoral research to be an expert in all three. So it's not that you have different people talking to each other. You have an interdisciplinary person. Yeah.
Well, I think inevitably I did want to ask about programming. And I mean, my original kind of background was in computer science. That's what I originally wanted to study. So I've been programming since I was in year 7. And, you know, it's a lot of years of just learning and then getting things wrong and slowly developing your skills. And I suppose a lot of either sort of amateur programmers like myself and even professional programmers, when they see how capable some of the AI is, there is a mixture of feelings. On one hand, it's brilliant because it can help you be more efficient, and you can spend less time sorting through loads of code trying to find a random logic error. But on the other hand, it does sort of, in some way, you feel a bit threatened by the use of the models. And I wanted to know if you have a more optimistic or pessimistic view on programming. Would your advice maybe be to people that considering learning it?
So I'm not sure where I stand on this yet. I've been thinking about it a lot. So there is something inherently satisfying about writing a piece of code that works from scratch, right? I think, and if you use AI to write your code, you lose that to some extent. And it's the same with maths, right?
Yeah.
If you work through a mathematical proof and you demonstrate to yourself that you've proved it, that's far more satisfying than asking a language model to do it for you.
Yeah.
So from a personal perspective, I think it's... it takes that away from you, which is a bit sad, right? Because those, often in research, those sort of like miniature wins are quite important for keeping your motivation going. On the other hand, it does speed things up massively, and I use models to speed up my coding.
Yeah.
And like you said, I do need to debug them. They don't always do what I want. Especially if I'm trying to do something completely novel. If I'm trying to do something novel, I have very poor success actually using models, and I usually revert to just doing it myself.
Yeah. Well, on the sort of the novel sort of idea, I think metacognitively there is a kind of, I think, maybe a misconception with, I think, how programming is learned. I think if you're looking at them like mathematics or physics in an undergraduate degree, so when I look at my like really huge thick physics textbook or just a book on proof or on calculus, I know that every single problem in those books has been solved before. You're learning those problems so that you can learn how to solve them, so that eventually when you get to something that's unsolved, you've built those metacognitive skills so that you can actually tackle those. Yeah. And I feel like in programming, as good as the models are, they're only as good as the training data that we provide them. So a lot of the models are really good at programming because the internet has a lot of code on it. But the only way it's going to improve is that if we write even better code so that it can train off of it, and you're kind of in this loop. And I suppose that's kind of how I keep justifying myself to keep learning programming. But
So I think there's an argument also for learning's sake.
Yeah.
And I do think that there's a sort of a cliff edge that we're possibly approaching. Maybe not super soon, but somewhere down the road. Because the reason that I'm able to debug the code that's given to me by a language model, or that I can revert to writing my own code, is that I can already code.
Yeah.
Right. So this is, like you, I've spent years developing the ability to write code. If I was starting to learn coding now, I'm not sure how well
when to integrate it.
Yeah, well, or how easy it would be to do that, right? If you are using an assisted coding system, you're going to learn in a very different way, and I don't know that necessarily you would gain the same depth of expertise. So there's certainly evidence in the literature, in the learning literature, I should say, about how too much AI assistance actually stops you learning so well.
Yeah, and it is, I would say, the same thing for maths and physics as well. I think if you rely on that to solve your problems, you're not going to get very far in your undergraduate degree.
Well,
I guess in the world of programming, I'm curious, at what point do you say to yourself, all right, I've mastered it, now I'm allowed to use it? It's not kind of obvious. And I'm struggling with this question because I don't know at what point I should be integrating it. I mean, maybe it's when you can code it yourself. You can code your own AI, and at that point, sure. But I don't. Yeah, it's. I think with programming, it's even more specifically a problem because it is. I think of all the things that AI is good at, it is quite good at writing code. But it seems to be only good at writing code that already exists. So there is this kind of weird paradox because I think if you're in a practical environment, there are situations in which you probably do want to use it to debug code, for example. But at what point, it feels like there is always a price you're going to pay for that. And it's sort of, I'm not sure when you could start allowing yourself to do so. And so, yeah, like you said, I'm not sure if learning with it is a great idea. It does seem like learning it the old-fashioned way of picking up a textbook or something or reading some documentation. Because it feels like the people that do that, so the old-school programmers, like they're the ones that really succeed in the end.
I think at the moment it's too early to tell how this is going to play out.
Which is scary.
It's, well, the technical fields are continuously evolving.
Yeah.
It's just something that you have to cope with, essentially. I think, the world does not stand still. Things do change. And it can be disconcerting, I think, if it's happening in an area that's closely related to what you do.
Yeah.
But essentially, it's you can't just freeze a moment and live in it forever, right? It's
I think it's also just more unnerving because it feels like every expert's got a different view on it, and so it's difficult for people to know what they should be learning. I suppose with physicists and mathematicians, they're still kind of doing their thing. Though people like Terence Tao have said that AI is changing the field of mathematics. So
yeah, I've seen he's very positive about it.
But I know some professors here are very negative about it. So it's not the way that I see it. It's just sort of carry on as if it's not there, and then maybe to slowly integrate it into your work.
I think slowly integrate it. I think also one thing that's probably going to be a bit of an equalizer going forwards is that I think the true cost of using these AIs, both in a financial and an ecological sense, is not yet well understood. Or is perhaps slightly obfuscated. And as that becomes more apparent, I suspect that more limited use of AI might be encouraged.
Are you concerned about the environmental effects of AI?
Yeah, I think it's important. I think at this point, we should consider the environmental effects of everything we do.
Yeah.
And and the computing behind the use of general language models is huge, both in training and at inference. So I think it is something that we should be very aware of.
Yeah, because I feel like there is kind of there is the optimistic side, and then there is the very real. Obviously, with any technological advancement, there is the environmental effect, think especially now
Mm.
with the scale of it, that is definitely, I think it could be, a lot of people are already sort of either skeptical about AI or outright boycotting it just because of the environmental effects and the effects it has on local environments. So maybe that could be a way to halt it, but I think all things considered, it's still worth learning programming. I think
So
someone would-
programming is more broadly useful than AI.
Yes.
So yes, I agree. Yeah.
So I don't think we could have spoke without talking about Artemis.
Artemis. I know nothing about Artemis, so this is a bad conversation.
Well, I find it interesting because it feels like it's, for a lot of young people particularly, it's either ignited or even reignited a kind of enthusiasm for astrophysics.
Okay.
I think on social media there's
Interesting.
a huge wave of comments saying, okay, now I'm going to go be an engineer, I'm going to go be a physicist. And I wonder
that's very
if
nice.
in the actual astrophysics departments, has there been a kind of resurgence in enthusiasm since, oh, we're going to the moon again?
Not that I've noticed, I have to say, although that may be because the astrophysics department here doesn't do that kind of astrophysics. So I mean, going to the moon is more space science than astrophysics.
In 2014, you were selected by the World Economic Forum and to join the young scientist community. Now, presumably you spoke, or at least met with some quite influential people. How do you sell either space exploration and space science to, let's say, the political class?
I think it's so in 2014, I think it was more difficult because there was less of a general awareness about the potential of space in 2014. So you were thinking sort of, pre the big SpaceX launches, pre Artemis, pre satellite configurations. It was the conversation wasn't really there yet, and so it was actually quite difficult. I mean, I wasn't trying to sell space in any particular way. I think I went to the World Economic Forum in quite a naive way, if that makes sense.
How so?
In the sense that I wasn't prepared fully for the level of salesmanship that people put into it.
Right.
Like it was very different from any environment that I'd been in previously academically. And it sort of, it opened my eyes a bit to how these things do get discussed at higher levels. I think these days selling the idea of space is much easier because people understand the economic importance of space, and they also understand the defense implications of space. So there's more of a conversation to be had. Like it's easier to start that conversation than it was in 2014. And although that said, I think there's still this misunderstanding about how technological development happens, because typically people only see the end of it, right? They see the result, and so there is an assumption that the big things that enabled this technological development happened just prior to that result and happened in the last stages of R&D, which is normally the high technical readiness level, the commercial level, and they attribute the success of that technology to the people who did that final bit there, to the industry behind it. And people have a tendency to forget the fundamental research that underpinned those companies' ability to actually do that R&D. And this, I think, is something that we see a lot in the space conversations, is that you see people talking a lot about the companies in the industry, but not about the fundamental research that underpinned it. And I think this is a somewhat universal problem for what are widely regarded as blue sky sciences like astrophysics, particle physics, for example, is that people don't see the translation, probably because it takes a long time, right, to get from the fundamental idea that initiates it to the result that people will, go and buy on the high street, essentially.
Or see in the sky.
Or see in the sky, yeah exactly. And because of that time scale, people don't have an appreciation for it, and so they think that you can neglect the bit at the bottom. And
which is the grunt research and
it's the grunt research. It's the research that doesn't have any immediate driving commercial outcome, right? Because it is the fundamental research. But if you get rid of that part of your research ecosystem, then maybe not immediately, but eventually you're going to lose the R&D at the other end.
Yeah.
Someone described it to me recently as it's like cutting off the roots and expecting the tree to survive.
Oh, right, yeah.
Yeah, it's same thing.
Yeah. Do you think that problem's gotten better?
Not at the moment. No, I think I think we can see society is very focused on, a number of large tech companies doing various things whilst pushing away from university-led research. And I think that is problematic.
Yeah, I think some of the misconception is that people they might not necessarily understand the importance of, let's say, just certain things in theoretical physics or in pure mathematics, unless they have an immediate causal effect on something in their lives. But it sometimes takes a while for those findings to prove themselves useful in some way.
Exactly.
I mean, it's not immediately obvious why researching prime numbers is useful. But then we realize, if we want to encrypt our credit card details, we need to know a lot about prime numbers.
Yeah.
And I wonder if this is a communication problem in terms of how we communicate to the public, or is it to those in Westminster, or...
I think partly it's the disparity between the amount of money that sits at the either end of the spectrum.
Yeah.
Because if you look at the way that money is spent in sort of the foundational academic research, it's spent on the research and not in publicity of the research.
Yeah.
And that's why people don't know about it. Every academic that I know goes out and gives public talks all the time, but essentially you're reaching a small local group of people, right?
Who are predispositioned to have that interest.
Yes, exactly, who are self-selected in some way.
Yeah.
Whereas if I'm, a large tech company, I have an entire publicity department that I invest a huge amount of money in.
Yeah, and
connections. So that's why people see it. So it's an imbalance question. But yeah, I mean, there are so many of these things that you can pick out. So I mean, one that I particularly like to highlight is GPS positioning on your phone, right? Every time you use Google Maps, if Einstein hadn't invented general relativity, that literally wouldn't work. You can look at particle physics and say World Wide Web. You can look at radio astronomy, Wi-Fi, right? It was literally people trying to move data on black holes around, and you get Wi-Fi. That's the sort of the longer term outcome, and it's but they're very difficult to make those connections. And of course, lots of other things happen along the way, but fundamentally, these are the things that
and
lead through.
I also think that even though on one hand we can see that a lot of these discoveries have a use down the line, but I don't think necessarily that it's the case that science is worth pursuing or useful because we think it'll have some sort of causal effect on our lives. I mean, obviously those things are great. We can create MRI machines and have Wi-Fi and such, but I think even particularly with things in pure mathematics, there is a kind of benefit in doing it just because it's difficult and because it's there to do. And I worry that, I mean, of course things like Artemis are great, but I wonder if without it would people have been more open to becoming physicists or to funding research. And I'm not quite sure how to sell it, because on one hand it's a great way to sell it by saying, oh look, if you look at black holes, we can create GPSs and such. But also it's not always easy to do that with every discovery. So how do you sell?
No, so I think I completely agree. I completely agree with you. These two things are separate. I think one is people's understanding of the value of the fundamental science, but then the other is the wider societal and personal impact of science, right? It's the increasing the sum knowledge of humankind is a good thing, right? It is a good thing, and so pushing against these big unknown questions like how did the first stars and galaxies form, when did it happen, these are things that increase our collective understanding of the universe that we live in, and Artemis, even though it's more local, right, it has that sense of wonder, right, and that's
which seems to it does seem to move people. It has a metaphysical importance to it. It's I'm not sure that the spirit that's behind scientific endeavor is much different to the spirit that is behind trying to improve society generally. I don't think it's a coincidence that as we've got more technologically advanced, we've also got better political systems and life in general improves. I don't think that those are just, I think people take that for granted.
Yeah, I think that science gives us a different perspective on our lives, right? The day to day, we end up doing the same mundane things.
Yeah.
And it's easy to forget what a small speck in the vast universe we are.
Yeah.
And then you see something and it reminds you and it gives you a perspective on not only your own life, but everything, right?
Yeah.
It gives you that widened perspective that just stretches your horizons and makes you think maybe there's something bigger.
Yeah.
Yeah.
I think just to finish off, do you have advice to, let's say, those young people or maybe people in undergraduate who are seeing things like Artemis happen and how to sustain their interest, not let that die out?
Yeah, I think my biggest advice would be to see everything as an opportunity.
Yes.
Even the things that are perhaps hard work and feel a bit dull when you're doing them.
Especially those.
Especially those. Yeah. And take time to, reflect on what you gained from things that you found more difficult to do. And I think that kind of self-reflection on your own growth as a person and towards a particular goal, if you're looking towards the space industry, I think that's a very important thing. It's much better than, just making sure you turn up all the time. Really think about, your place in this and how it's benefiting you. Yeah, and then grab those opportunities.
Yeah.
Yeah.
So, I think embracing the hard stuff, I think is good, because it feels like these fields, it is mostly just getting things wrong and then adjusting it. That's a feature, and I don't think that's a bug.
I think this is I think this is one of the things that I'm quite optimistic about with the rise of AI.
Yeah.
I think to some extent we've got into this sort of pattern of, we go to university, we get a degree, that helps us get a job, and that sets us up, and that becomes the driving force, and then we forget the other possibilities, right? Is that, I'm not naive. I realise that people need jobs and need to earn money, right? So if you're going to go to university to help you get a job, that's fine. But once you're there, you're at university, right? So take advantage of it and really, invest yourself in the learning process and personalise it to yourself. And I think that I'm optimistically hoping that the utility of AI that takes away the hard stuff from us will actually help us to reflect more on why we should relish the hard stuff.
Yeah.
Yeah.
Because, maybe more so than anything else, I think particularly in mathematics, I think when writing a proof, for example, struggling, trying something, not working, plugging into this formula, doing this, that's the bulk of the experience. But the great thing is you only have to get it right once. Yeah. So, and that feeling is pretty unmatched.
Yeah, exactly. So, yeah. Yep.
Wow, yeah, that's. I'm glad we finished on an optimistic note. Professor Scaife, thank you very much.
Well,
That's
you're
great.
very
Thank you
welcome.
so
Thank you
much.
for the conversation.
Yeah.